Hi, everyone. Thanks for joining us today. Hope you're enjoying the summer. I'm Twinkle, the chair of publications for the CAN section of the ACS organization. And today we have Manny with us from Abstrax. And Manny is sharing about his first author paper on temperature-controlled butane extraction. And I will let Manny take it away, but just so you guys know, Manny graduated from Cal Poly Pomona with his bachelor's in chemistry recently, and then was able to publish his first author paper. So we just want to give him so many props for that.
Yeah, thank you, Twinkle, for the introduction. I'm a research chemist here at Abstrax Tech. I've been fortunate enough to be a part of many peer-reviewed papers, including one of Twinkle's. But yeah, today we're going to be talking about temperature-controlled butane extraction and how it minimizes your wax co-extraction while preserving your cannabinoids and terpenes. So I'm going to be going over a couple slides today, and let's get into it. So what is cannabis composed of? I feel like a lot of us have a pretty good understanding of this, but here we have a Sankey diagram. And essentially cannabis is mainly composed of cannabinoids. One of the biggest ones is going to be THCA, and then you have your other cannabinoids like CBDA and THCV, as well as you have your aroma compounds. So this is something that Abstrax is really familiar with and something we've studied a lot in the past. So we have your terpenes, which gets subdivided into monoterpenes, monoterpenoids, sesquiterpenes, and sesquiterpenoids, as well as your flavorants. Flavorants being your esters, alcohols, and ketones, as well as your canosulfur compounds. So in the past, we have published this paper, which we dive into canosulfur compounds, as well as this one, where we kind of dive further into more flavorant chemistry, as well as finding these tropical thiols. And then we have this one as well, where we kind of look at phenotypes and predict different aroma characteristics. We find more tropical thiols and kind of figure out what makes cannabis smell cheesy. But today we're not going to be talking about aroma compounds. So this is kind of different from what Abstrax has done in the past. Today we're going to be focusing on this other section in the Sankey diagram, specifically when it comes to waxes. So what are these waxes and lipid fraction that has always been talked about? And so there are many ways to consume cannabis products. We have your topicals, your capsules, edibles. You can dab it, vape it. But for many of these, you can't just use flower. You have to make an extraction of cannabis concentrates. So in order to do this, you have a couple options, right? So cannabis concentrates, you have your HTE, which is like a high terpene butane hash oil. You have distillate cannabis oil. You have crystal-like products like sugar, which is THCA. And honestly, the list goes on, right? I don't even have a majority of them on here, but today we're going to be specifically talking about HTE, which is a high terpene extract of butane hash oil, as well as some Rick Simpson oil, which is an ethanol extraction. So there are many ways to produce these methods, right? You have number one being hydrocarbon extraction, which can be pentane or butane or a mixture depending on your SOP. You have ethanol extraction. This is a way to make Rick Simpson oil. You have CO2 extraction as well as impression. CO2 extraction isn't really used as commonly in the industry anymore, just due to the favorability of, butane having pulling all your terpenes and cannabinoids and leaving a lot of the other phytochemicals behind. But there are common challenges when it comes to any of these. You have unwanted phytochemicals that still pass through. You have solvent hazards. Hydrocarbon extraction is very dangerous, so you need to be very safe about it. And you have terpene loss, right? Terpenes, you want to preserve them depending on your final product that you want to make to keep all the aroma and flavor. The questions we are going to be answering today is, how does extraction temperature affect butane hash oil? How does temperature affect terpene profiles in butane hash oil? And how does solvent affect the extract? So looking at butane hash oil versus an ethanol extract. So when doing sample procurement for this study here, we tried to go across our the exotic cannabis aroma spectrum. This is kind of like a figure we kind of designed ourselves, but kind of classifying all cultivars in these three categories. Kind of simplified things. So you have your sweet cultivars, your prototypical cultivars, and your savory cultivars. So trying to get across the whole array, we chose three different cultivars: GMO, Oreos, and Rainbow Belts. We tried to procure roughly around 50 pounds of fresh frozen flower of each of these. Unfortunately, for Rainbow Belts, we weren't able to procure enough, and therefore we weren't able to do all experimental studies on it. So that one got unfortunately put to the side, but today we're going to be focusing on Oreos and GMO specifically. So if you don't know how butane hash oil is made, here's a simple schematic, kind of following the diagram. Let's start at step one, where you pack all your fresh frozen flour into a mesh-like bag, which we call a sock. This fresh frozen flour is stored at a really negative 80 degrees Celsius freezer. You pack your sock down. In step two, you start chilling down your butane to your desired temperature. In step three, you lower your sock into the column of your butane extraction system, and you let it soak for a desired time. After all, it passes through the columns, you end up with your butane hash oil at the bottom. You put these in some Pyrex glasses. In step five, you let the Pyrex glass sit in a controlled environment, letting all the residual butane evaporate out since it has such a low boiling point. During step five, you have step six, where a lot of your solids start crashing out into solution. This solid is mainly THCA, or sugar. After that, you separate the two fractions, and we gently melt the butane hash oil so that all THCA left in there is below 20%. So kind of converting the THCA into THC. And we do multiple HPLC testing to make sure it falls within that lower than 20% range, just so that it doesn't crash out into solution again, especially like in an end consumer product. So extraction conditions that we were looking into, specifically looking at temperature, is chilling our butane down to three different temps. So we have our hottest temperature being negative 9 degrees Celsius, our middle temperature being negative 32 degrees Celsius, and our coldest temperature being negative 46 degrees Celsius. So I know it looks weird in Celsius, but in industry standards, a lot of them use Fahrenheit. So it would be converted to 15 degrees Fahrenheit, negative 25 degrees Fahrenheit, and negative 50 degrees Fahrenheit for your coldest. And we did this across GMO, Oreos, and as well as using leftover material to make Rick Simpson oil with all of these. After we made the material in bulk, we did UV vis to look at the color, HPLC to look at all cannabinoids, and we ran these across our two-dimensional gas chromatography system, which is paired with an FID, a SCD, and a TOF mass spec. So diving into the results here, here's some UV vis data, kind of looking at the color. And for the most part, there is not much to see until you get to the lambda max of 663. For both the GMO and the Oreos, you see this little bump arise around this lambda max. And this was very curious for us because we're trying to figure out what it might be. And when we do the UV vis with our Rick Simpson oil, you can see that lambda max at 663 has a huge spike. Specifically due to its green color of Rick Simpson oil, as you can see there in the vial to the right. And when doing a quick literature search, you can see that the lambda max for chlorophyll A does fall in between 430 and 662. You have two peaks for the chlorophyll A. So this gave us the conclusion that that bump in our actual BHO still has some chlorophyll in there. But they do decrease as you decrease your temperature. But we kind of want to dive further into this in the future to see if there's any sensory aspects that we can see. But one of the main things that really was impacted by the temperature was visually you can see the fats and waxes, right? But starting in here in figure A, you have your HTE yield. So you have a slight increase in yield, as you increase your temperature. So the colder your temperature is, the less yield you have. Your total cannabinoids are roughly the same, kind of linear. Same with your aroma compound percentage. So we couldn't make any huge correlations with total cannabinoids lost or gained, as well as your aroma compounds, as you increase or decrease your temperature to your desired, to the experimental temperatures, right? But one thing you did notice from the product, and especially in figure D, when looking at the oil itself, at the top of figure D, at the hottest temperature of -9 degrees Celsius, you see all these white little specks. And then at the bottom, with the coldest temperature being -46 degrees Celsius, it looks like a really clean butane hash oil. And so we were trying to figure out what these specs were. And so we did a winterization method, which is essentially just getting a little bit of your material, putting methanol in there, and then sticking it in a freezer. We stuck it in a -80 degrees Celsius freezer, when you do that, all your waxes and fats pretty much just crash out of solution and kind of settle down at the bottom of the vial. And so you can see here in GMO, you can see the white specks kind of like from left to right almost disappear. In Oreos, you can see a huge dramatic shift of how much waxes and fats are in the first vial at the hottest temperature and almost disappeared at your coldest temperature, -46 degrees Celsius. But one thing we're very curious is, like, what are these waxes and lipid fractions made of? And so we ended up fractioning off all of these with the Buchner funnel and purifying them in order to run them on a two-dimensional gas chromatography system. And paired with an alkane standard, we were able to see that a lot of these are just long-chain alkanes, which are insoluble in methanol. And they range from C17 all the way to C32. They might be bigger, but I couldn't risk our method being too long because it would destroy our columns. So our method was around 90 minutes long, holding max temperature of 270 degrees Celsius for around 30 minutes. And any longer, it would just degrade our column way too much. So the longest alkane chain we saw was C32. And so here is an example of what we're seeing on our GC. So here's the alkane from C25 to C31. Kind of falling in the Oreos, -9 degrees Celsius. You see the same peaks fall in line as well. But as you decrease in your temperature, you're seeing those peak intensities drop, which is kind of like showing apples to apples what we saw visually when we did the winterization method. And so in figure B and C here, you have everything kind of stacked up as to what actual alkanes have the highest concentration. And that being your C29 and C27 are going to be the ones in highest concentration. So your nonacosane and your heptacosane for all samples, whether it be Oreos or GMO. In this two figures here, we have compositional differences between the samples. So in figure A, it's just a simple bar graph kind of showing all the subclasses, monoterpenes, monoterpenoids, your sesquiterpenes, flavorants, and waxes. So one thing I did want to note here is that in figure A, when you're looking at your ethanol extracts for both GMO and Oreos, that blue bar for monoterpenes essentially just disappears. And this kind of makes sense too, because when you're doing ethanol extraction, you have to boil off all of the ethanol. So common methods to do that is doing rotovap. And when you're doing this, all your monoterpenes follow a similar boiling point to your ethanol. So as you're boiling off your ethanol to make a clean product to ingest, you're boiling off all those monoterpenes as well. So you are just missing that fraction when you're making a Rick Simpson oil as far as aroma class goes. But for the rest, you can see the bar graphs hold similar monoterpenes, sesquiterpenes, but you see that black fraction with the waxes. That one is increasing or decreasing depending on your temperature. In figure B and C, these are log slopes. So essentially what these are showing is a positive correlation. So anything at the top of these graphs heading to, let me get my links here. So anything at the top of these graphs going to the right are positively being impacted as you increase your temperature. So anything at a hotter temperature, these compounds here are getting produce more. So it's going to be your non-nicotine, heptacotane, and trioctane. So that's going to be C31, C29, and C27. And so looking at this in a different lens, you have your principal component analysis figures. So this principal component analysis figure, you have your ethanol extracts in here, your fresh frozen flour kind of having a similar chemical matrix, and then all your butane hash oils being over here to your right. So this kind of makes sense because your butane hash oils are way more concentrated in your terpenes and all your aroma classes, so they are going to be more concentrated and more similar on this side. And then your ethanol extracts and fresh frozen being less concentrated, they're going to stay on the left. When you explode this right side, you're going to get figure B. So here you have your GMO more tightly packed and your Oreos over here to the left, which has more separation in the Y direction. And that's mainly because you have that huge dramatic shift on all the alkanes getting decreased as you decrease your temperature. So the hotter your butane hash oil was, the more alkanes you had. So your non-nicotine, your heptacotane. That way, these are going to be your hotter temperatures. This is your middle range temperature, and this is your coldest temperature down here. So following this study, we really wanted to see if all of these alkanes aerosolize in a vape cart. This was important for us to see, and we partnered with our collaborators who are known as Active, formerly known as AVD. They're a vape cart manufacturer, and they have this really awesome vaping simulation system down the road from us. So we headed down there in order to test these carts with the actual butane hash oils inside of the carts. We did this in quadruplicate. Essentially, what the vaping simulation system does is it mimics the puff topography of a human pool based off of their own studies to replicate, the correct rate of pull and the length of time. So we did this at the same voltage for every cart, and essentially collected these in a filter pad, getting all these filter pads and then running them on a two-dimensional gas chromatography system, and only looking for specifically if the alkanes that are in solution are getting transferred into the aerosolized phase and ending up on the pad itself. And what was really interesting here is that essentially they did. So wax and aerosol phase, so these are the collected pads, and how many of these alkanes or waxes were found in the end product. So the hotter the temperature, the more you have, and then the colder, the less, right? But the biggest one that was important is going to be figure C here, which is showing you almost a 1-to-1. So it's an R-squared value of 0.965, but essentially is the waxes in HTE that started in the cart, and then the waxes in the aerosol phase, which is what we caught on the pad. So almost everything that was in the cart ended up on the actual pad, which is something to bring up and something of concern, right, for longer term studies, which we'll get into. But questions we have about these waxes is essentially, where do they come from, right? Why are they known to be in cannabis, or are they known to be in nature at all? And they are. So they're not only native to cannabis. Epicuticular waxes is a wax layer kind of known to be found on these plants in order to protect it from other things as environmental stressors, whether it be water stress, light source, abrasion. They naturally form in order to protect the plant from all the environmental stressors. One thing that was still curious to me, which is for a later study, is trying to understand, why did Oreos at hotter temperatures produce way more than GMO, right? So at the hottest temperature, we saw that Oreos was sitting around like 22% alkane, and then GMO at the hottest temperature was around 8%. So they were grown in the same farm, so it wasn't like farm to farm variation. But right now, my current hypothesis is that it can be something due to bud morphology. Oreos being a bigger bud, having more surface area for all of these to be grown, all these alkanes to be grown. But further study needs to be done with this, looking at multiple different cultivars and trying to understand how this works. But in conclusion, we identified the long chain alkanes and butane hash oil, kind of figuring out what this wax and lipid fraction is that, is kind of like a nuisance to the industry, because a lot of people end up getting these and then they'll do the winterization, adding in that second step in order to eliminate them so that they don't end up in your consumer product. We understood how, different solvents affect your end product, whether it be butane or ethanol, whole different chemistry going on as far as all the phytochemicals you're pulling. One is more favorable to terpenes and cannabinoids. Ethanol is a way harsher solvent, so it's pulling a lot of those other phytochemicals with it, like your chlorophyll, your fats and stuff. But it still has its very medicinal benefits to that. So we finally understand as well that going colder in your temperature is going to decrease these alkanes. So that's something that is like the biggest thing we kind of wanted to push onto the industry, is that, when you go hotter, you're going to get more yield. But more yield doesn't always equal more dollars, because when you're doing the more yield method, you're probably going to end up with a lot of these alkanes, waxes, and fats. But usually you go to that intermediate step where you're like trying to take those out by doing the winterization step. So that's another solvent risk if you're not handled properly. That adds in like all the labor to do it. But if you just go colder from the beginning, you're able to just eliminate getting those in your final concentrate for butane hash oil. And that's about it. Future works is for sure looking more into the toxicology studies of, these alkanes ending up in the aerosol phase. They're naturally found to be known in cannabis, but when you do a concentrate, you're concentrating everything. You're concentrating your terpenes, your cannabinoids, and you're concentrating these alkanes as well. So there is going to be a limit to how much can be ingested, right? If you guys are interested in reading the full paper, it is open access at ACS Omega. But yeah, I would like to give my acknowledgments and thanks to Dr. Ian Oswald, Twinkle Periani, Dr. Chenshang AI, and all authors on the paper, and also the whole team at Abstrax Labs who helped me do all the extraction on all this fresh frozen flower. You guys have any questions?
Great job, Manny. Thank you for presenting. Go ahead, Jerry.
Well, I had a couple of comments, not so much questions. You want to go ahead? I'll wait.
Looks like Evan has a question.
Thanks, Manny. This is great. It's nice to see the ultimate results of all this work. I know you've been at this for a minute. Did you look at flower morphology and that impact? Did you like both the density of the flowers themselves as well as the potentially the cuticle thickness of the terpene glands heads, right? Because these alkanes are the cuticles essentially,
Yeah.
aren't they?
Correct. Yeah. But I personally haven't done that. That's definitely something for future work, especially looking at not only 2 cultivars, but a variety of cultivars in order to really understand, why certain ones have more than others.
Cool. Thank you.
I'll ask a question that I know people are wondering, which is, do we see these alkanes in other extracts besides BHO and ethanol extractions?
Yeah, for sure. One of the other big ones for sure going to be in rosin or impression. So you're definitely going to see them in there as well.
Yeah, this is Jerry King. Can you hear me?
Yeah, I can hear you, Jerry.
Okay. Just a few comments. You regarded, your technique you were concerned about the upper temperature limit using the GC method. And you might want to look at supercritical fluid chromatography. There was a lot of work done even the 1980s into the 90s. We have a few papers in it I could send to you, where we used the capillary SFC mainly. And it's called SIM distillation. And you can extend the carbon number, the hydrocarbon profile substantially, where you're cut off a bit by the the thermal constraints of the GC method. The second thing is we had what's called my age is showing here. We had up in Alberta, Canada, I supervised 5 different essentially teams, senior research teams, and one of them produced a 432-page report. And part of it involved an extrapolation of room temperature dated using a polynomial fit as to what the best temperature would be for freezing out the waxes by conventional cold ethanol extraction. And the extrapolated value turned out to be about minus 80 degrees centigrade, which seems to commensurate with your theme that the colder the temperature needs to be looked at. Third comment is that you showed the UV this absorption spectra for chlorophyll. I've been saying this for some time. We did CO2 extraction on a material and found that the actual species that's extracted, and I would expect it to be similar for hydrocarbon butane extraction, isn't really chlorophyll, which is a metallized porphyrin structure. There is no metal ion there, but there is a demetallized form of chlorophyll, has almost identical, the same UV spectra. And it does extract in CO2. I don't know what the hydrocarbon extraction solvent would look like. But we did a lot of wax capillary SFC work on commercial waxes, insect waxes, you mentioned on one of your plates, and also just a number of, profiling experiments using capillary SFC. I could send you the paper. I think you'd find it kind of interesting. Final comment, I was impressed by your work. I went to the Omega ACS article and picked up on it. And I was considering mentioning it. I head off to a super green conference in Sapporo, Japan tomorrow. And I thought about, mentioning your ACS Omega article, as a good reference, with some leading work in the area. Anyway, that's all I have to say.
Awesome. I appreciate all the kind words, Jerry, and all your comments. I mean, you're a big expert on the field, specifically in extraction. I have you as cited in a lot of the papers, specifically your big review that you had released recently. So appreciate the kind words.
Is your email on the ACS Omega thing?
It should be. It should be, as well as my boss's, who's Dr. Ian Oswald, so he can forward it to me as well.
Okay, I may forward something to you.
Thank you.
Great job, Manny. We have one more question in the chat, which Tara is asking if you could go back to the slide with the winterization data, the lowest butane temperatures. I think they want to know if you did the ethanol extraction at a colder temperature, or if it was at what that temperature was.
Sorry, this one here, or
let's see. I think this one.
This one. As far as the ethanol extraction goes, I did do it at a cold temperature. The ethanol was chilled down to negative 30 degrees Celsius in a freezer. So I let that just pure ethanol sit in a freezer at negative 30 degrees Celsius for a couple hours. So I got to temp. Then I got the fresh frozen flour and I soaked it in there for roughly I can't recall how long, but it wasn't too long. But I let it soak in there, and then I separated the actual solid and liquid phase into two separate reservoirs. And then it was essentially the liquid phase that was then rotovapped and gave me the Rick Simpson oil.
Awesome. I think that answered their question.
Yeah, another question I had, you mentioned, I thought that you used methanol versus ethanol. Did you use the methanol at some point, or did you just use ethanol for the?
So yeah, so in the actual winterization process, in order to visualize all the waxes and fats and crashing the waxes and fats to fall in solution, I use methanol. Since methanol is like not soluble with the alkanes, or the alkanes are not soluble in methanol, they do crash out into solution, specifically when you freeze it. And then you'll get like these pooling effects of the waxes and fat, very fluffy. But yeah, ethanol was used to make Rick Simpson oil.
Okay.
Awesome. Thanks so much. If anyone has any other questions, please put them in the chat. If Manny wants to share his email here, he definitely can, or anything else that you want to plug, Manny, please feel free to, and I can drop the link to the paper in the chat.
Yeah. I sent my email in the chat for my work email. So if you feel free to send me any questions, or, Jerry, I'd appreciate if you could send me any articles that you think would be of interest.
Okay. When I get back from Japan.
Sounds good. Yeah, man. Enjoy your trip.
One last thing before we go. Tara wants to know that the waxes were present in all the samples, correct? But just in different quantities.
Correct. Yeah, just different concentrations, or microgram per milligrams. And that's kind of shown in this slide specifically. So, yeah.
I think what Tara is getting at is, there could be potentially a way to use this information to extract, and then there be no waxes in the final product if you were able to monitor for these.
For sure. Yeah. And I mean, the one big hypothesis or answer we kind of have right now is just go colder, right? I know it is more expensive to chill your chillers to a certain, degree, because more electricity needs to be used, but then it's going to save you a lot of other, post-processing steps in order to remove and remediate the end concentrate, right? So there's pros and cons to everything.
Yeah, well, that's just like the way it goes in manufacturing. When you have a lot of steps, optimizing those steps is really key. And I think this is a really, really great example of real world experiences showing that for things that people in the industry are actually needing to see on the everyday production line. So thank you again for joining us. And I hope you can join us again when you have more data to share. And we'll be sharing this on our YouTube, so it'll live there forever.
Awesome. Well, thank you for having me. Really appreciate it.
Yep. All right, everyone. Have a great day. We'll see you next time.